Look at this saucepan boiling on the stove. The body is entirely metal, but the attached handle is carved out of wood. This diagram shows exactly why. Heat energy from the fire transfers rapidly up through the metal body, because aluminum is an excellent thermal conductor. But that heat stops abruptly at the handle, because wood acts as an insulator, keeping your hand safe from burns. Whether you are working with natural resources like timber from a forest or synthetic plastics formed in a lab, every material operates under strict physical rules. These rules dictate exactly how a material behaves under stress, heat, or moisture. Because of these fixed rules, a designer cannot simply pick whichever material looks best. The primary job is to diagnose exactly what physical limits a material has, and then match those limits to the demands of the structural problem. Here we see a worker shaping wet clay. Notice how easily it yields to physical pressure, taking on the strict rectangular shape of a brick and holding that new form perfectly. This unique ability to be molded and retain a new physical shape is called plasticity. Now, let's observe how different materials handle sudden impacts. In this setup, a heavy hammer drops forcefully onto a solid block of mild steel. The steel absorbs that massive shock. It sustains a visible dent, but structurally it remains entirely whole. This ability to absorb heavy physical shocks without breaking is the definition of toughness. If we drop that same hammer onto a block of dry clay, the result is completely different. The clay instantly shatters into multiple sharp pieces. We call this severe tendency to shatter immediately upon impact brittleness. Notice how a material's state changes the physical rules it follows. The wet clay from before had high plasticity, but drying or firing it removes that moldability, leaving the material extremely brittle. Knowing exactly where a material crosses the line between being tough and being brittle allows engineers to build structures that hold up under immense pressure, instead of collapsing. In everyday conversation, people often say a material is hard when they mean it is unbreakable. In engineering, these are entirely separate concepts. This diagram sets up a simple scratch test to prove the difference, using samples of pine wood, mild steel, and glass. When we drag the iron nail across the pine wood, it cuts a deep physical groove. Doing the same across the mild steel leaves only a faint scratch. But when the nail drags heavily across the glass, it leaves 0 marks. The glass completely resists surface abrasion. In strict engineering terms, this means glass possesses supreme hardness. However, if we drop a heavy hammer onto that exact same piece of untouched glass, it shatters instantly. Extreme hardness does not mean a material is tough. Hardness is exclusively about resisting cuts and scratches. Let's apply this to a real problem. If you are building a roof frame that must support heavy iron sheets during a severe windstorm, which material should you choose? Dry clay, or glass, or mild steel? The correct choice is the mild steel, or perhaps a strong timber. The roof frame requires the specific property of toughness so it can flex and absorb the wind shock without snapping. If you substitute a hard material for a tough material in structural engineering, your frame might resist a few scratches, but it will suffer a collapse the moment it takes a heavy impact. This exploded diagram of a traditional Ugandan charcoal stove shows these properties in action. The inner architecture is fired clay, an extreme heat insulator containing intense temperatures. Because clay is brittle, a tough recycled metal casing wraps tightly around the interior to protect it. This photograph of the Kampala Taxi Park shows this strategy scaled up. Thousands of vehicles rely on tough steel bodies to endure constant physical shocks. This matrix tracks our baseline properties. Mild steel offers toughness for vehicle frames and burglar bars. Aluminum provides thermal conductivity without rusting, ideal for saucepans. Clay gives us high plasticity when wet and heat insulation when fired. Plastic provides a waterproof, lightweight barrier. Brilliant designers do not force materials to perform against their chemical nature. Instead, they diagnose the problem, understand the limits of the materials, and leverage strict combinations of physical properties to build safe, highly functional products.